Right now, an object from another star system is approaching Mars at 61 kilometers per second, and the only people talking about it are amateur astronomers and one very vocal Harvard professor. Strangely enough, NASA has been very quiet on the subject, while the European Space Agency has only released a few technical blog posts here and there. Meanwhile, hundreds of defense officials just gathered at Quantico for a meeting nobody will explain. Coincidence? Maybe. But here's what makes 3I Atlas different from every other cosmic visitor. It's threading through our planetary neighborhood, like it knows where it's going. Mars on October 3rd, Venus in November, Earth in December, Jupiter next spring. One trajectory, 4 planets, and institutions that suddenly forgot how to throw a press conference. And it gets better. Right when this interstellar object reaches peak solar heating at perihelion, Earth's telescopes go blind. Solar glare blocks observation for weeks. Mars orbiters become our only eyes. Stay until the end, because what we discover in December, when Earth can finally see again, might depend entirely on what we're willing to question now. NASA's silence isn't random. Let's find out why. Part 1. The Paradox. 3I Atlas is sliding past Mars right now, and NASA's keeping strangely quiet. Think about what that means for a moment. We have a visitor from another star system, only the 3rd confirmed interstellar object in human history, making its closest approach to the red planet in the next few days. This isn't some distant celestial curiosity passing billions of miles away. We're talking about an object that originated in an alien solar system, travelled for potentially millions of years through the cosmic void, and is now threading the needle through our planetary neighbourhood. And yet, if you go looking for live press conferences, breathless NASA announcements, or wall-to-wall coverage from the usual science media outlets, you'll find almost nothing. Just sparse website updates, a few technical blog posts, some Hubble Space Telescope observations quietly uploaded to archives, a JWST preprint that dropped on our archive with minimal fanfare, ESA putting out frequently asked questions pages like they're answering questions about routine satellite maintenance. This is the paradox we're riding. Maximum celestial drama, minimum institutional noise. Let me give you the breadcrumbs, because they exist, you just have to know where to look. July 2nd, 2025. The Minor Planet Center officially designates this thing as 3I Atlas, with the formal designation C/2025 N1. That 3I tells you everything. It's the 3rd interstellar object ever confirmed, following 1I/Oumuamua back in 2017 and 2I/Borisov in 2019. The Atlas survey in Chile spotted it first on July 1st, already inbound on a hyperbolic trajectory that screams not from around here. By the time they calculated the orbit, it was clear this thing is moving at roughly 61 kilometers per second relative to the Sun, following a path that could never be closed by our star's gravity alone. It came from somewhere else. August 7th brings Hubble's update. They've constrained the nucleus size, upper limit around 5.6 kilometers across, possibly as small as a few hundred meters. The nucleus itself isn't directly resolved, just wrapped in a glowing coma of gas and dust. But that measurement matters, because size tells you mass, and mass tells you how much this thing can push itself around without gassing jets. Then comes August 25th, when the JWST team drops their preprint. This is where things get chemically interesting, and we'll dive deeper into this later, but for now, know this. The coma around 3I Atlas is absolutely dominated by carbon dioxide. The ratio of CO2 to water is roughly 8:1, among the highest ever measured in any comet, anywhere. That's not normal. That's weird. As September rolls into October, ESA announces that Mars Express and the ExoMars Trace Gas Orbiter will conduct an observation campaign from October 1st through 7th, with closest approach on October 3rd at about 30 million kilometers. 30 million kilometers might sound like a lot. It's roughly 80 times the distance from Earth to the Moon. But in astronomical terms, for an interstellar object making a drive-by of another planet, that's threading the needle. Then comes the blackout. Not a blackout in the sense of cover-up, but a blackout in the sense of geometry and physics. As 3I Atlas approaches perihelion, its closest point to the Sun, around October 30th at approximately 1.4 astronomical units, Earth loses its view. Solar conjunction. The object passes too close to the Sun from our perspective, and our telescopes either can't point that direction safely or get saturated by solar glare. We go blind, right when things get most interesting. We won't reacquire a clear view until early December. So here's the situation. We have Mars-based instruments watching during the approach in early October, then a month-long gap where almost nobody Earthside can see what happens at perihelion. Then we pick up the trail again in December when it's already outbound. And during this entire sequence, the official communications from the major space agencies have been technical, restrained, almost bureaucratic in their dryness. Now, you might say that's just how science works, and you'd be partially right. Scientific caution is a virtue. Nobody wants to pull an alien megastructure like what happened with Tabby's star, only to have it turn out to be dust. Error aversion is baked into institutional culture. Multiple observation epochs, peer review, cross-checking against models, all of that takes time. But here's where the tension lives. The gap between what institutions are saying and what amateurs, small observatories, and a handful of high-profile scientists are shouting about. While NASA posts sanitized updates to their blog, independent observers with smart telescopes and Las Cumbres network access are posting raw images showing peculiar tail structures. While ESA publishes frequently asked questions pages, Avi Loeb, yes, that Avi Loeb, the Harvard astronomer who won't shut up about Oumuamua being potentially artificial, is out there floating the possibility that 3I Atlas could be worth a closer look for exactly the same reasons. The silence isn't total, it's selective, and that selectivity creates a vacuum, and vacuums get filled with speculation, with pattern matching, with people connecting dots that may or may not belong in the same picture. And then there's Quantico. We'll get to that in detail later, but you need to know about it now because it's part of the optics, part of the narrative web that's formed around this object. In late September, right as 3I Atlas is making its Mars approach, US defense leadership gets summoned to Marine Corps Base Quantico for an unusually large short-notice gathering. The official purpose? Vague. The media framing? Rare, abrupt, urgent. The White House downplays it as routine, but the timing is what makes people's eyebrows go up. Is there any proven connection between Quantico and 3I Atlas? No. Zero public evidence. But coincidence in timing is the conspiracy theorists' favourite food, and right now they're being fed a 7-course meal. So here's the thesis. The through line we're going to follow. This story isn't about explaining what a comet is. You probably know what a comet is. This is about what lives in the gaps between official data and public communication, the gaps in observational coverage, the gaps in what we can see versus what we can infer. This is about timing and geometry, and the uncomfortable fact that we're going to be blind during the most critical window. This is about who fills those gaps when institutions stay quiet, and what happens when amateur astronomers, science communicators, and contrarians become the loudest voices in the room. We're going to separate peer-reviewed data from preprint speculation from outright rumour. We're going to label what's confirmed, what's plausible, what's exotic, and what's bonkers. And we're going to flag exact dates, exact measurements, exact sources, receipts for everything. But first, we need to establish baseline reality. What do we actually demonstrably know about 3I Atlas? Where are the cracks in the public record, and why do those cracks matter? Let's find out. Part 2. What we do know, and the cracks in the public record. Let's start with the stuff nobody disputes, the hard numbers, the confirmed observations, the things you can look up in multiple independent databases and get the same answer. Discovery and certification first. The Atlas survey in Chile, asteroid terrestrial impact last alert system, an automated sky scanning network designed to catch near-Earth objects before they become a problem, flags an unusual moving point of light on July 1st, 2025. Within 24 hours, the Minor Planet Center, the official international clearinghouse for asteroid and comet observations, runs the orbital calculations and confirms what Atlas suspected. This thing is on a hyperbolic trajectory. The eccentricity of the orbit is greater than 1, which is the mathematical way of saying it's not bound to our Sunday. It came from interstellar space. They designate it 3I Atlas, officially C/2025 N1. The C means it's showing cometary activity. It has a coma. It's outgassing. It's not just a dead rock. At the time of discovery, it's inbound at roughly 61 kilometers per second relative to the Sunday. For perspective, the fastest spacecraft humanity has ever built, the Parker Solar Probe, tops out around 192 kilometers per second at perihelion. But it's getting gravity assists, and falling toward the Sunday 3I, Atlas is carrying that 61 kilometers per second from interstellar space, slowing down as it climbs into our sun's gravity well. The geometry and timeline tell their own story. The object makes its closest approach to Mars on October 3rd, 2025, passing about 30 million kilometers away. That's roughly 0.19 astronomical units. An astronomical unit for reference is the average Earth-Sun distance, about 150 million kilometers. So 0.19 AU is close, astronomically speaking. Not collision course close, not even particularly dangerous close, but close enough that Mars-based instruments can get a decent look. Then it continues inbound toward perihelion on October 30th, at approximately 1.4 astronomical units from the Sun, well inside Mars's orbit, but nowhere near Earth. At its closest to Earth, which happens much later in its trajectory, it's still about 1.8 astronomical units away. There is zero hazard to our planet. Let's be absolutely clear on that, because the last thing we need is doomsday panic. This is not an impact scenario. This is an observational opportunity. Hubble's contribution came on August 7th, delivering an upper limit constraint on the nucleus size. They can't directly resolve the nucleus. It's too small and too far away, but they can measure the brightness of the coma and model how much solid material you'd need to generate that much gas and dust. The answer? Probably no bigger than 5.6 kilometers in diameter, possibly as small as a few hundred meters. That range is huge in terms of implications. A 5-kilometer nucleus would be a respectably sized comet, something with substantial mass and gravitational self-binding. A few hundred-meter nucleus would be more like a rubble pile, barely held together, vulnerable to tidal forces and rotational breakup. We don't know which it is yet. The coma is visible, glowing beautifully in reflected sunlight and self-emitted gas fluorescence, but the nucleus itself remains unresolved, a tiny dark seed wrapped in a fuzzy cloud. JWST delivers the chemistry, and this is where things start getting genuinely strange. The James Webb Space Telescope, our infrared monster, turns its spectroscopic instruments toward 3I Atlas in late August. The results land on ArcGIV as a preprint, not yet peer-reviewed but authored by mission team members, which gives it substantial credibility. What they find? The coma is absolutely dominated by carbon dioxide, with water, carbon monoxide, and carbonyl sulfide also present. The CO2 to H2O ratio is approximately 8 to 1, plus or minus 1, 8 parts carbon dioxide to 1 part water. That is, to put it scientifically, extremely unusual. Most comets in our solar system are water-dominated. Water ice is the primary volatile, with CO2 and CO as secondary components. 3I Atlas flips that script. It's more fizzy soda than steam, more dry ice than water ice. ESA operations add another layer to our observation window. The European Space Agency, which operates Mars Express and the ExoMars Trace Gas Orbiter, currently in orbit around Mars, announces an observation campaign targeting October 1st through 7th, with peak observations timed to the October 3rd closest approach. These orbiters carry spectroscopic instruments designed to study the Martian atmosphere, NOMAD, and ACS on the Trace Gas Orbiter, SPICAM, and OMEGA on Mars Express. Those instruments can be turned toward 3I Atlas to capture time series spectra of the coma, measuring how the gas composition changes as it approaches the Sunday. This is our best real-time window, because of what comes next. The observability gap is the elephant in the room. From late September through November, Earth-based observatories lose their view. 3i Atlas approaches perihelion on October 30th, and from our vantage point, it's passing too close to the sun's glare. Solar conjunction. Telescopes can't safely point in that direction, or if they do, the signal gets swamped by scattered sunlight. SOHO and STEREO, solar observatories in space, might catch some broad dust dynamics, but they're not designed for detailed spectroscopy of small comets. So we go blind right when the object is getting its maximum heating, right when internal ices are being baked and outgassing is at its peak. We won't reacquire a clear view until early December, by which point it's already outbound and cooling. Now here are the cracks, the things that matter narratively, even if they don't matter scientifically. First, there's the cadence and tone of official updates. NASA's posts about 3i Atlas read like technical blog entries, dry, factual, aimed at an audience that already knows what perihelion means and doesn't need hand-holding. There are no live press briefings, no dramatic countdown clocks, no join us for the flyby hype videos. ESA's frequently asked questions page is similarly restrained. It's information, sure, but it's not showtime. Compare that to how agencies covered the Perseverance, Mars landing, or the DART asteroid impact, or even the James Webb first light images. Those were media events. 3i Atlas is getting blog posts. Second, the datasets are scattered. If you want the full picture, you need to stitch together information from the Minor Planet Center circulars, JPL Horizon's ephemeris outputs, NASA's Hubble pages, the RIXI preprint server, and ESA's Mars mission pages. There's no central hub, no everything you need to know about 3i Atlas landing page with live updates. That fragmentation means casual observers have to work to find information, and when information requires work to find, fewer people find it, and the perception of silence grows. Third comes the media asymmetry. Mainstream science outlets, your Nature News, your Scientific American, your Space.com, have covered 3i Atlas, but cautiously. The headlines are measured. New interstellar visitor detected. Mars orbiters to observe unusual comet. Meanwhile, the more speculative takes. Is this an alien probe? Why is NASA hiding 3i Atlas? Travel faster and further on social media. It's not that the speculative takes are more numerous, it's that they're more shareable. Caution doesn't go viral, mystery does. Why does this matter? Because low drama official communication plus high drama timing equals a perception of silence, even when there's technically no silence at all, and that perception becomes the story. The absence of spectacle gets read as intentional suppression, when it might just be institutional culture meeting a scientifically fascinating but not yet definitive observation campaign. But here's the thing, even setting aside the narrative optics, there are genuine scientific oddities here. The composition is weird, the behavior is weird, and weird doesn't mean artificial, it means we don't fully understand it yet, which is exactly what science is for. So let's get into the weirdness, the data-backed, peer-reviewed, or at least pre-printed anomalies that make 3i Atlas worth all this attention in the first place. Part 3. Anomalies in behavior and composition. Here's where we separate unusual but explicable from genuinely strange, from probably has a natural explanation, but we don't know what it is yet. Let's start with the chemistry, because that's the most data-rich anomaly. The JWST spectroscopy gives us a carbon dioxide to water ratio of approximately 8:1, 8 parts CO2, 1 part water. To understand why that's remarkable, you need to know what normal looks like. Most comets in our solar system, the ones born in the Kuiper belt or the Oort cloud, the ones that have been falling toward the sun and outgassing for billions of years, have water as the dominant volatile. Water ice makes up the bulk of the frozen material. CO2 is present, sure, but usually in smaller quantities, maybe 10 to 30% of the water abundance. Carbon monoxide can be abundant in some comets, especially those from the Oort cloud, but even then, water usually dominates. 3i Atlas flips that. It's like finding a person who breathes carbon dioxide and exhales oxygen, biologically backwards, thermodynamically confusing, demanding an explanation. So what are the explanations? One possibility: this is a comet that formed in a region of its birth star's protoplanetary disk, where carbon dioxide ice was more stable than water ice. Different stars have different luminosities, different radiation environments, different snowline locations where volatiles condense. It's possible that 3I Atlas formed in a colder, more carbon-rich environment than our solar system's comet factories. That would make it genuinely alien in composition, not just in origin, a snapshot of different stellar chemistry. Another option: water is there, but it's locked deeper in the nucleus, insulated by a layer of carbon dioxide and dust. Carbon dioxide sublimates, turns directly from solid to gas, at much lower temperatures than water ice. As the comet approaches the Sun, the outer layers start venting CO2 while the water ice beneath stays frozen. We're seeing the fizz before the steam. If this is true, we'd expect the water signal to increase post-perihelion as solar heating penetrates deeper and unlocks the buried H2O. There's also a third possibility, more speculative. The nucleus has a patchy, heterogeneous surface. Some areas are water-rich, some are CO2-rich, and right now, during the Mars flyby and approach to perihelion, the CO2-rich side is facing the Sunday. As the nucleus rotates, and we know it's rotating because the light curve shows variations, different compositions get exposed, and we see episodic changes in the outgassing pattern. This would explain not just the high CO2 abundance, but also the light curve irregularities that multiple amateur observers and small observatories have reported. These irregularities are real and documented. 3I Atlas doesn't brighten smoothly as it approaches the Sunday. There are flickers, little brightness variations that suggest episodic outbursts or jets. Now this isn't unprecedented. Comets do this. Comet Hartley 2 did this. Comet Tempel 1 did this. When you have a nucleus with patchy volatile distribution, and it's rotating, you get jets that turn on and off as different areas face the Sunday. But the pattern for 3I Atlas seems more erratic than usual. Some observers describe it as breathing, as if the comet is pulsing with activity. That's evocative language, maybe too evocative, but the underlying data, the brightness variations, are real. Here's a hypothesis worth considering. Maybe the nucleus has a thin dust crust, and subsurface gas pressure builds up until it cracks the crust, creating a sudden outburst. Then the crust reforms, pressure builds again, rinse and repeat. This kind of thermal wave model, where heat slowly penetrates and creates delayed, pulsed activity, could explain the episodic jets and the dominance of low-temperature volatiles like CO2 early in the approach. It's speculation, but it's testable speculation, the kind that makes predictions we can check. Another weird thing, the sunward plume. Some images from amateur observers show what looks like a tail or plume extending toward the sun, not away from it. That sounds wrong, right? Solar radiation pressure and the solar wind should push dust and gas away from the sun, not toward it, and they do. But there's a phenomenon called an anti-tail, an optical illusion that happens when you're looking at a comet's dust trail edge-on. Dust particles spread out along the comet's orbit, and if your viewing angle is just right, the trail can appear to point sunward even though it's actually following the orbital path. This has been observed in other comets. Comet Arend-Roland in 1957 had a famous anti-tail, so the sunward plume is probably geometry, not propulsion. Probably. But it looks exotic, and exotic-looking things get attention. Size uncertainty remains a problem, and it's more important than it might seem. Hubble gives us an upper limit of 5.6 kilometers, but that's based on assumptions about albedo, how reflective the surface is, and how much dust versus gas the nucleus is producing. If the nucleus is darker than assumed, it could be larger. If it's more reflective, and smaller. If it's producing more dust than expected, the mass estimate goes down. Until we get better astrometry and can measure non-gravitational accelerations precisely, tiny changes in the orbit caused by outgassing jets, acting like thrusters, we won't pin down the mass, and without mass, we can't fully understand the dynamics. Let's contrast this with 2I/Borisov, the previous interstellar comet, because the comparison is illuminating. Borisov was discovered in 2019 and observed extensively during its pass-through the solar system. Borisov was carbon monoxide rich, which was unusual, but its overall composition was broadly comet normal. Water was present, CO2 was present, the ratios were within the range of solar system comets. Borisov felt familiar, like a comet from someone else's Oort cloud. 3I Atlas feels different. The extreme CO2 dominance, the episodic activity, the high carbonyl sulfide abundance, these are all pushing the boundaries of what we consider normal for comets. Why would interstellar ices be odd? Because they formed around a different star, in a different chemical environment, possibly at a different epoch in galactic history. The interstellar medium, the gas and dust between stars, has regions with different compositions depending on the history of supernovae, stellar winds, and radiation fields. A protoplanetary disk that formed in a region enriched with carbon from previous generations of stars might produce comets with higher CO2 content. A disk that formed in a colder region, farther from the birth star, might preferentially condense carbon dioxide over water. We're seeing the fingerprint of alien stellar chemistry, written in ice. Here's another speculative hypothesis worth flagging. What if the nucleus has internal pockets of volatile rich material, like bubbles or cavities? As the surface heats and sublimates, these pockets get exposed, and suddenly you get a localized outburst of gas that wasn't connected to the surface before. The nucleus breathes because it's structurally heterogeneous, not just compositionally. This would be testable with time series spectroscopy. If the Mars orbiters catch a sudden spike in CO2, or a new species appearing briefly, that's evidence for pocket outbursts. One more thing worth noting: carbonyl sulfide, OCS. This is a trace species, a minor component, but JWST detected it. Carbonyl sulfide is relatively rare in solar system comets, though not unheard of. Its presence suggests sulfur, chemistry in the formation environment, possibly involving hydrogen sulfide or sulfur dioxide precursors. If 3I Atlas is enriched in sulfur-bearing molecules, that tells us something about the composition of its birth disk, about the chemical pathways that were active when it formed. So here's the summary. 3I Atlas is compositionally weird, behaviorally erratic, and visually deceptive. It's almost certainly a natural comet, but it's a natural comet that's testing the boundaries of our models. And that's before we even talk about the trajectory, the orbital geometry, and the uncomfortable fact that its path through the solar system looks almost too convenient, almost like it was planned. Which brings us to the question everyone wants to ask but feels silly asking. Is there any chance this thing is deliberate? Part 4. Trajectory and Intent. Probing the alignment hypothesis. Let's talk about the orbit, because this is where the speculation gets spicy and where we need to be extremely careful about how we frame things. 3I Atlas is travelling in a retrograde orbit, meaning it's moving opposite to the direction that planets orbit the Sunday. That's not unusual for interstellar objects. They can come in from any angle with any orientation. But here's what is notable. Its orbital inclination is only about 5 degrees from the ecliptic plane. The ecliptic is the flat disk in which Earth and most of the other planets orbit. 5 degrees off that plane is nearly coplanar. It's like a car merging onto a highway almost perfectly aligned with the traffic lanes, except the traffic is going one direction and the car is going the opposite way. Why does that matter? Because most interstellar objects we'd expect to encounter would come in at steep angles. Space is three-dimensional, and the majority of trajectories through the galaxy don't happen to align with any particular star's planetary disk. If you're shooting pool and you randomly throw balls at the table from any direction, most of them won't skim along the felt. They'll come in high or low, but 3I Atlas is skimming the felt. Now, before we jump to conclusions, there's a selection bias to consider. Our sky surveys are concentrated along the ecliptic because that's where most of the interesting solar system objects live. Asteroids, comets, near-Earth objects. We point our telescopes where the action is. That means we're more likely to discover interstellar objects that pass through the ecliptic plane simply because we're looking there more often. It's like looking for your keys under the streetlight, because that's where the light is. The keys might be elsewhere, but you'll never find them if you don't look. So the fact that 3i Atlas is nearly coplanar might just mean it's the kind of object our surveys are biased toward finding. But let's say it's not just selection bias. Let's say there really is something interesting about the trajectory. What makes it feel, to some observers, almost mission-like? The Mars flyby happens on October 3rd at 0.19 astronomical units. That's close for an interstellar object. Not unprecedentedly close, but close enough to sample the Martian environment, the magnetosphere, the escaping atmospheric gases, the dust. If you were designing a probe to study Mars, you might fly by at a similar distance to get remote sensing data without the expense and complexity of orbital insertion. Then it continues inbound to perihelion on October 30th at 1.4 AU. That's inside Mars's orbit but outside Earth's, a region that gives you good solar heating without getting too close to the sun's disruptive tidal forces. It's the sweet spot for observing a comet's activity. After perihelion, the trajectory takes it past Venus at 0.65 AU on November 3rd. Then, past Earth at 1.8 AU on December 19th. Then a distant pass of Jupiter at 0.36 AU on March 16th, 2026. Venus, Earth, Jupiter, 3 major planets, visited in sequence. If you were planning a grand tour, a flyby mission to sample multiple planetary environments, this is roughly the kind of trajectory you'd design. Not exactly, because a real mission would optimize for closer approaches and specific scientific targets, but the general architecture, the sequential encounters, has a mission profile feel to it. This is where we have to pump the brakes and talk about the base rate fallacy. The base rate fallacy is when you see a pattern and assume it's meaningful without considering how likely that pattern is to occur by chance. Yes, 3i Atlas passes near Mars, then Venus, then Earth, then Jupiter. But interstellar space is big, and objects enter the solar system from random directions with random velocities. Some of those random trajectories will, by pure chance, happen to pass near multiple planets. We don't notice all the trajectories that don't do this because they're boring. We notice the ones that do because they fit a narrative we recognize, the narrative of intentional exploration. It's the same cognitive trap that snared some researchers with one I/Oumuamua. Oumuamua had a weird elongated shape and exhibited non-gravitational acceleration. It deviated from a purely ballistic trajectory. Some scientists, most notably Avi Loeb, suggested it could be an artificial light sail, a probe from an alien civilization riding on solar radiation pressure. The mainstream explanation is that it was outgassing, venting jets of gas that acted like tiny thrusters, but the gas itself wasn't detected, which made the outgassing hypothesis less satisfying. The debate still hasn't been fully resolved, and probably never will be, because Oumuamua is long gone and we only had a few weeks of observations. 3i Atlas gives us a longer observation window, but it comes with its own ambiguities. The key question: will it show non-gravitational accelerations that can't be explained by outgassing? Non-gravitational accelerations happen when a comet vents gas preferentially in one direction, creating a thrust. This is normal. Comets do this all the time. But the magnitude and direction of the thrust should be consistent with the observed outgassing. If you see a bright jet, you should see a corresponding acceleration. If you see a lot of CO2 and water being ejected, you can calculate how much momentum that gas carries and predict how much the comet's trajectory should change. Here's what we'll be watching: precise astrometry before and after perihelion. Astronomers will measure the position of 3i Atlas in the sky with high accuracy, fit those positions to an orbital model, and look for residuals, deviations from the predicted path. If the residuals are small and consistent with the outgassing we observe, case closed, it's a comet doing comet things. If the residuals are large and don't match the outgassing, or if the direction of the acceleration seems wrong, then we have a puzzle. The Oumuamua lesson is this: don't overfit sparse data. We had maybe 20 data points for Oumuamua's position, spread over a few weeks, and from that we tried to infer shape, rotation state, composition, and acceleration mechanisms. That's hard. Errors compound, assumptions matter. 3i Atlas gives us more data, months of observations, multiple instruments, spectroscopy, But we still need to be disciplined about what we claim. One thing we won't get: resolved images of the nucleus. Even with our best telescopes, 3i Atlas is too far away and too small for that. We'll infer its properties indirectly: light curves to estimate rotation and shape, spectra to measure composition, astrometry to track non-gravitational forces. It's like trying to understand a person by listening to their footsteps, their voice, and the shadow they cast, without ever seeing them directly. So is the trajectory evidence of intent? No. Is it suggestive enough to warrant careful measurement? Absolutely. The null hypothesis, that 3i Atlas is a natural comet on a random interstellar trajectory that happens to pass near several planets, is still overwhelmingly the most likely explanation. But the non-null hypothesis, the exotic possibility that something deliberate is going on, is testable. We can measure it. We can rule it in or out with data. And speaking of things that are testable but not yet tested, why is the US military gathering at Quantico right when this is all happening? Is that meaningful? Or is it just another pattern we're reading into because patterns are how humans make sense of chaos? Let's find out. Part Chink, Quantico. Late September 2025. US. Defense leadership, Joint Chiefs, senior Pentagon officials, figures whose names you'd recognize if you follow military affairs, get summoned to Marine Corps Base Quantico for a meeting. Not a routine briefing, not a scheduled conference, an unusually large, short-notice gathering described by multiple outlets as rare and abrupt. The official purpose? Vague enough to be meaningless. Strategic discussions, ongoing operations, the kind of language that tells you nothing. The White House press secretary, when asked, downplays it. Routine stuff, nothing to see here. Defense leadership meets all the time. And that's true, they do. But the optics matter. The size of the gathering, the suddenness, the secrecy around the agenda, all of that creates a perception of urgency. And urgency invites speculation. Reuters covers it. Al Jazeera covers it. It's not fringe reporting, it's mainstream news. But the mainstream news also doesn't have details because details aren't being provided. So what fills the gap? Inference. Pattern matching. And here's the pattern people are matching. A major interstellar object is making its closest approach to Mars, and simultaneously the US. Military brass is convening in secret. Coincidence? Or coordination? Let me be crystal clear about what we can and cannot say. There is zero public evidence connecting the Quantico meeting to 3i Atlas. None. No leaked memos, no whistleblower statements, no on-the-record comments from officials linking the two. If you're going to make that connection, you're doing it based on timing alone, and timing is the weakest form of evidence. It's circumstantial at best, coincidental at worst. But let's also acknowledge why people make that connection, because it's not irrational, it's just not evidential. Space domain awareness is a military concern. The US. Space Force exists, tracking objects near Earth and beyond, understanding potential threats or anomalies, coordinating with civilian space agencies. All of that happens. If an unusual object were behaving in ways that warranted a security briefing, you might expect exactly this kind of gathering. You might expect it to be short notice, because the Mars flyby window is time-sensitive. You might expect it to be large, because coordinating across commands requires senior leadership. And you might expect the agenda to be vague, because security matters often are. Consider what it would actually mean if the Quantico meeting were space-related. You'd need to coordinate observations across military and civilian assets, ground-based radar, space-based telescopes, signals intelligence platforms. Getting everyone in a room to align priorities makes sense. You'd need to decide who points what, where, who gets access to which data, and how to communicate findings without compromising sensitive capabilities. That's the kind of coordination that requires face-to-face meetings with senior leadership, especially if there's genuine uncertainty about what you're looking at. There's also the communications angle. If there were genuine uncertainty about what 3i Atlas is, and you didn't want to create public panic or diplomatic complications before you had answers, you might establish guidelines for what gets shared publicly and what stays internal until confirmation. That's not suppression in the sinister sense. It's risk management. It's the difference between saying, we're tracking an unusual object and studying it, versus, we don't know what this is and we're concerned. The first is responsible. The second creates panic. But there are limits to what makes sense here. A defensive posture against a comet? That doesn't track. 3I Atlas is not a threat to Earth. The trajectory is well characterized, fully understood. Even if it were headed our way, which it absolutely isn't, we have no capability to deflect or destroy an object of that size on that timeline. The DART mission proved we can nudge a small asteroid with months of warning and careful planning, but an interstellar object moving at 61 kilometers per second? We'd need years of lead time and technology we don't currently possess. So if Quantico were about 3I Atlas, it wouldn't be about defense. It would be about observation and information control. There's also the signal detection angle, and this is where things get interesting from a what-if perspective. If 3I Atlas were transmitting radio signals or exhibiting unambiguous signs of artificial propulsion, that would leak. Not immediately maybe, but eventually. Too many people would be in the loop. Radio astronomers, mission scientists, international partners. The SETI community would be vibrating with activity. You can't keep a signal detection secret when half the amateur radio community has dishes pointed at the sky. The infrastructure of modern astronomy is too distributed, too international, too open for that kind of containment. So the absence of that kind of activity, the lack of urgent SETI observations, the lack of coordination across radio telescope networks, tells us something. It tells us that if there's anything unusual about 3I Atlas, it's not screaming its presence through the electromagnetic spectrum. Now let's talk about the alternative explanations, the ones that have nothing to do with comets from beyond our solar system. The Reuters reporting mentions ongoing discussions about readiness and operations. Late September is the end of the fiscal year for the U.S. government. Budgets get finalized, next year's priorities get set, command structures get reviewed. It's bureaucracy season. A large gathering for strategic planning isn't unusual, it's annual. There's also the geopolitical context, which we can't ignore just because space is sexier. Tensions in multiple theatres, Eastern Europe, the Middle East, the South China Sea, require coordination and contingency planning. A gathering of Joint Chiefs could easily be about conventional military readiness, not exotic space objects. And then there's personnel. Military leadership changes, retirements, promotions, these require face-to-face coordination. Maybe someone's rotating out of a critical command and there are succession discussions. Maybe there's an internal investigation or review that requires senior leadership to convene. None of that generates press releases, but all of it generates meetings. The timing might be short notice because someone's retirement got moved up, or because a geopolitical situation required immediate attention, or because budget deadlines shifted. Mundane explanations are usually correct, even when they're less satisfying than exotic ones. So why include Quantico in this narrative at all? Because the audience will hear about it. Because ignoring it would be dishonest, like pretending there's no elephant in the room. Because the optics, the timing, the secrecy, the institutional reticence from both military and civilian space agencies create a perception of connection, whether or not that connection exists. Here's the responsible framing. Quantico happened. 3I Atlas is happening. The two events are temporally coincident, but evidentially disconnected. If future reporting reveals a concrete link, we'll update. Until then, treat it as two separate stories that happen to occupy the same moment in time. But here's why the narrative won't die, why it can't die. The absence of information creates a vacuum, and vacuums get filled with speculation. When NASA gives you blog posts instead of press conferences, when the military convenes in secret and says nothing to see here, when the mainstream media covers both stories but doesn't connect them, while social media absolutely does connect them, that's when the narrative takes on a life of its own. And narratives have consequences. They shape public trust. They influence funding decisions. They determine how seriously people take the next interstellar visitor, or the next UAP report, or the next unusual astronomical event. If this turns out to be a completely natural comet and a completely routine military meeting, and the speculation was just noise, then we've learned something about how stories propagate in the absence of clear communication. If it turns out there was more to either story than we were told, then we've learned something about what institutions choose to disclose and when. Either way, the gap between official silence and public curiosity is the story within the story. It's not just about what 3i Atlas is, it's about who gets to define what it is, and how that definition gets communicated, and what happens when the communication pipeline is too slow or too cautious for the speed at which questions travel. Which brings us to the people filling that gap: the amateurs, the independent observatories, the preprint servers, and the occasional contrarian scientist with a platform and an appetite for the exotic. They're the ones posting images, running calculations, and keeping this story alive while the institutions draft their carefully worded statements. So, let's talk about who's watching, what they're seeing, and how to tell. Signal from noise. Part 6. Leaked data, shadow communications, and amateur front lines. Here's the thing about modern astronomy. You don't need a billion-dollar telescope to contribute meaningful data anymore. You need a good camera, a decent mount, dark skies, or the ability to stack images to beat light pollution, and patience. The barrier to entry has collapsed. Smart telescopes that can plate solve automatically, match star patterns to catalogues and tell you exactly what you're looking at, cost less than a used car. Image stacking software is free. Orbital mechanics calculators are online. The tools of discovery are democratized. And that means the people discovering things, or at least documenting things first, are often not the people with NASA badges. Take the Las Cumbres Observatory Network. This is a global network of robotic telescopes, some of them operated by professionals, some accessible to advanced amateurs through observation time proposals. When 3i Atlas was first confirmed, Las Cumbres instruments were among the first to start tracking it continuously. Images started appearing online, raw frames, stacked composites, time-lapse sequences, showing the comet's motion against background stars. These weren't NASA press releases. These were data dumps from observers who had time allocated and wanted to share what they were seeing. Some of those images show the coma structure clearly. Some show what looks like a faint sunward plume, that anti-tail effect we talked about earlier. Some show brightness variations consistent with rotational modulation or episodic outgassing. And some show artifacts, cosmic ray hits, tracking errors, stacking misalignments, that look interesting until you understand what you're looking at. This is where the signal-to-noise problem begins. Not every image is created equal. Not every observer calibrates their equipment the same way. Not every analysis accounts for atmospheric extinction, or air mass, or the difference between total brightness and surface brightness. So, when someone posts a spectacular image of 3i Atlas with a dramatic tail structure, you have to ask, is that real, or is that a processing artifact? Is that a single exposure or a stack? What filters were used? What's the exposure time? What's the seeing condition? Reliable repositories exist, and knowing where to look matters. The Minor Planet Center publishes circulars, official notifications of astrometric measurements submitted by observatories worldwide. Those are vetted. If you report a position, it gets checked against other observations, and if it's wildly discrepant, you get questioned. JPL Horizons gives you ephemerides, predicted positions and velocities based on orbital solutions. Those get updated as new astrometry comes in, and you can see the uncertainty shrink over time. These are trustworthy sources. Then there are preprints. The ArcGive server is where astronomers post papers before peer review. This is crucial for fast-moving events like comets, because peer review takes months, and by the time a paper is published, the object might be gone. The JWST spectroscopy result we've been citing, that's a preprint, not yet peer-reviewed, but authored by mission team members, people with their names on the instrument, people whose careers depend on getting it right. That gives it substantial credibility, even without formal peer review. It's not gospel, but it's close. And then there's the noise. Screenshots of unattributed images. Claims of giant nucleus based on someone misreading a brightness measurement. Speculation about mass based on incomplete astrometry. Videos with ominous music and no sources. These spread fast because they're emotionally resonant, because they fit narratives people want to believe, because they're shareable in ways that, here's a link to the Minor Planet Center circular, just isn't. Let's talk about visual gotchas, because this is where a lot of misunderstanding happens. Anti-tails and projection effects are perfect examples. When you look at a comet, you're seeing a three-dimensional structure projected onto a two-dimensional sky. The dust tail, which is pushed by solar radiation pressure, streams out behind the comet along its orbital path. But depending on your viewing angle, that tail can appear to curve, or bend, or even point sunward. It's geometry, not physics, defying itself. Comet Arend-Roland in 1957 had a famous anti-tail that looked like a spike pointing toward the Sunday. Turned out it was just the edge of the dust sheet seen nearly edge-on. Same thing is happening with some of the 3i Atlas images. If you want to understand what you're seeing, you need to know the phase angle, the angle between the Sun, the comet, and your viewpoint. You need to know the scattering properties of the dust. You need to model the tail geometry in 3 dimensions and then project it onto the sky. Or you can just look at it and go, "Whoa, sunward tail, that's weird," and post it without context. Guess which one happens more often? How to read an ephemeris becomes actually useful if you want to follow along. Go to JPL Horizons, plug in the target DES equals 3i Atlas. Set your observer location and date range, and it spits out a table. The key columns: R is the Sun-comet distance in astronomical units. Delta is the observer comet distance. SOT is the Sun observer target angle, which tells you the phase angle. Elong is the solar elongation, which tells you how far from the Sun the comet appears in your sky. When elongation drops below 20 degrees or so, ground-based observation becomes difficult. Small changes in R and delta matter because of the inverse square law. Brightness falls off as 1 over distance squared, so a comet at 1 AU is 4 times brighter than the same comet at 2 AU, all else being equal. But all else is never equal because comets are active. They brighten as they approach the Sun, not just because they're closer, but because they're outgassing more. Disentangling those effects requires careful photometry over multiple epochs. Coordinated amateur campaigns are doing exactly this kind of work. Networks of observers taking images on the same nights, using consistent filters and calibration stars, building up light curves that track brightness over time. This is real science. This is publishable data, if done carefully. And the best amateur campaigns are doing it carefully. They're stacking images to beat noise. They're using apertured photometry to measure just the nucleus region. They're accounting for atmospheric extinction. It's not casual snapshots. It's systematic observation. But then there's the amplification problem, and this is where things get messy. A careful analysis that concludes, we see a rotational period of approximately 14 hours, with episodic brightening consistent with localized jets, doesn't make headlines. A sensational read that says, "Comet behaving erratically, possible alien probe," goes viral. And once it's viral, it's everywhere. It's in Reddit threads, YouTube videos, Twitter discussions. The signal gets buried under the noise, and separating them becomes a full-time job. Here's a prediction worth making. Expect more anonymous Mars orbiter leak images during the Earth blackout. When ground-based telescopes can't see 3i Atlas anymore, and the only assets with a view are the ESA Mars orbiters and maybe some solar observatories, that's when the information vacuum is deepest. And vacuums get filled. Someone will post an image claiming it's from Mars Express, or the Trace Gas Orbiter, claiming it shows something anomalous. Before you believe it, ask, is there metadata? Is there a mission timestamp? Does the image match the expected resolution and spectral range of the instrument? Does ESA confirm it? Most likely, it'll be fake, or misattributed, or a real image from a different mission misidentified. The bar for evidence needs to be high, especially when official channels are quiet. So, what's the takeaway for viewers trying to follow this responsibly? Stick to sources with names attached. MPC circulars, JPL Horizons updates, mission team preprints on RXIV, official ESA, and NASA posts. If someone makes a dramatic claim, ask for their data. Ask for their methodology. Compare it against other observers. If it's real, it'll be reproducible. If it's noise, it'll be an outlier. And remember, spectacular doesn't mean accurate. Sometimes the most important data is the boring data, the astrometric position measured to 1/10 of an arcsecond, the spectrum showing exactly the expected lines, the null result that rules out an exotic hypothesis. Science progresses as much by eliminating possibilities as by confirming them. But why are the institutions so quiet in the first place? Is it pure scientific caution, or is there a security dimension we're not seeing? Let's dig into that. Part 7. Institutional Reticence. Science versus Security. Why isn't NASA throwing a press conference? Why isn't there a live stream of the Mars flyby? Why does the most exotic interstellar visitor in years feel like it's being treated with the enthusiasm of a routine satellite launch? Let's start with the science culture reasons, because those are the most mundane and probably the most accurate. Error aversion runs deep in institutional memory. Organizations like NASA remember the faster-than-light neutrinos from CERN in 2011 that turned out to be a loose cable. They remember the arsenic life forms that turned out to be contaminated samples. They remember every time someone went public with a dramatic claim and then had to retract it. Those memories breed caution. Before you announce something extraordinary, you need extraordinary evidence, and extraordinary evidence takes time to accumulate. With 3i Atlas, you need multiple observation epochs to characterize the orbit precisely. You need to rule out measurement errors, tracking errors, contamination from background stars. You need to fit non-gravitational acceleration models, and those models require data from before and after perihelion. You can't fit a curve with 2 data points. You need a dozen, or 50, or 100, and even then your model has error bars. So the institutional instinct is to wait, to gather more data, to let peer review do its job before making bold public statements. Communications pipelines are also slower than social media makes them seem. Public information officers at NASA work on schedules. They coordinate with mission scientists, legal teams, international partners. A single blog post might go through 5 rounds of review before it's published. That's not suppression, it's bureaucracy. It's making sure you don't accidentally say something that contradicts what ESA is saying, or that reveals proprietary instrument capabilities, or that uses language that could be misinterpreted. It's the price of being a large, multi-stakeholder organization. And frankly, NASA has communicated about 3i Atlas. They've posted updates, they've shared Hubble results, they've linked to the JWST preprint. It's just not showtime. It's not a media event. And maybe that's appropriate, because we don't actually know if there's anything extraordinary here yet. We know it's interesting. We know it's worth studying. But interesting doesn't always mean press conference worthy. Now let's talk about the security culture possibilities. And I want to be very careful here because we're moving from documented explanations to speculative ones. Space domain awareness is a real thing. The US Space Force, along with other nations' space programs, tracks objects in orbit and beyond. They monitor satellites, debris, asteroids, anything that could pose a threat or require coordination. If an unusual object enters the solar system on a trajectory that brings it near Earth or its assets, that gets flagged. Not necessarily because it's dangerous, but because it's anomalous, and anomalies get attention. There is no public indication that 3i Atlas warranted a defense posture. Let me say that again. No public indication. No statements from Space Force. No congressional briefings. No leaked memos. If it were being treated as a potential threat or as something requiring classified analysis, we'd expect tighter information control, yes, but we'd also expect the lack of information to be more total. The fact that we have JWST preprints, Hubble posts, ESA observation plans, all of that argues against a security lockdown. But here's where it gets murky. Absence of evidence isn't evidence of absence. Just because we don't see signs of security involvement doesn't mean there isn't any. It just means we don't see it. And that's where speculation lives, in the gap between what we can observe and what might be happening beyond observation. Precedents are mixed and worth examining. When 1I/Oumuamua was discovered in 2017, there was no indication of military involvement. It was a civilian discovery, civilian observation campaign, civilian analysis. Avi Loeb's exotic hypotheses got attention, but they were academic debates, not security matters. When the Pentagon released UAP reports in 2023 and 2024, those videos of Navy pilots encountering unexplained aerial phenomena that was explicitly a defense issue. But UAPs in Earth's atmosphere are different from astronomical objects millions of kilometers away. They're different domains, different jurisdictions. If there were a security dimension to 3i Atlas, what would it look like? Probably not overt, probably something like classified sensors taking additional measurements that don't get shared publicly. Coordination between civilian and military space surveillance assets. Maybe restrictions on what mission scientists can say in public forums, not because the data is classified, but because the methods used to collect it are. The challenge is that all of this is indistinguishable from normal operations. Civilian-military coordination happens all the time. NASA shares data with Space Force for tracking purposes. Instrument capabilities are often sensitive, not because of what they observe, but because of how they observe it. Aperture sizes, spectral ranges, signal processing techniques that could be reverse-engineered by adversaries. Bureaucratic choke points slow everything down, and this matters more than people realize. If you need sign-off from NASA, ESA, the National Science Foundation, and Department of Defense before releasing a statement, you're going to wait. Each agency has its own review process, its own equities, its own risk tolerance. A statement that NASA is comfortable with might be too revealing for DoD, or too definitive for ESA scientists who want more data before committing. So you either release bland consensus language that satisfies everyone and excites no one, or you wait until the data forces a conclusion. There's also funding optics to consider. JWST and Hubble are oversubscribed. For every hour of telescope time that gets allocated, 10 proposals get rejected. If you're a mission scientist, you don't want to overpromise on a target that might turn out to be a dud. You don't want to generate public expectation for detailed nucleus imagery when you know you can't deliver it. Better to manage expectations downward and let the data speak for itself. Here's a speculative hypothesis worth considering. Maybe the language around 3i Atlas is being scrubbed to avoid intent, framing until after perihelion data is in. If you say, this object is making a close pass of Mars, that's factual. If you say, this object is targeting Mars, that's loaded. It implies agency, deliberation, design. And if you don't know which framing is correct, you stick with the neutral one until the data resolves it. Another speculative possibility, strategic silence during the Earthside blackout. If you can't observe, and you don't know what's going to happen at perihelion, why create public expectation for real-time updates? Better to stay quiet, let the Mars assets collect their data, wait for the glare to clear, and then release a comprehensive picture. That way, you avoid the problem of live interpreting incomplete data and having to walk back statements later. The takeaway: absence of drama does not equal absence of data. It might mean the opposite, that there's so much data being collected and analysed that institutions are drowning in it, and public communication takes a backseat to actually doing the science. If you want to follow what's really happening, look to the preprints, look to the mission logbooks, look to the observation schedules. Those tell you more than press releases ever will. But here's the irony. While Earth goes blind at perihelion, we have a forward operating base. We have assets at Mars. And for a brief window, Mars becomes the most important vantage point in the solar system. So let's talk about what the Mars orbiters can see, what they can't, and why that matters. Part 8. Mars as the Observation Relay. October 1st through 7th, 2025. While Earth-based telescopes lose 3i Atlas in solar glare, Mars becomes the front row seat. ESA operates 2 spacecraft currently orbiting Mars, Mars Express, which has been there since 2003, and the ExoMars Trace Gas Orbiter, or TGO, which arrived in 2016. Both were designed to study Mars, its atmosphere, its surface, its geology, but both carry instruments that can be turned toward other targets when opportunities arise. And 3i Atlas, passing within 30 million kilometers on October 3rd, is absolutely an opportunity. Let's talk about what they're equipped to see. TGO carries NOMAD, the Nadir and Occultation for Mars Discovery Instrument, and ACS, the Atmospheric Chemistry Suite. Both are high-resolution spectrometers designed to detect trace gases in the Martian atmosphere. They work in infrared and visible wavelengths, picking out the spectral fingerprints of molecules like water, methane, carbon dioxide, carbon monoxide. When you point those instruments at a comet, you get the same kind of data: coma composition, gas production rates, isotopic ratios, if the signal is strong enough. Mars Express has SPICAM, spectroscopy for investigation of characteristics of the atmosphere of Mars, and Omega, a visible and infrared imaging spectrometer. Omega can build up maps of surface composition by looking at how different wavelengths of light get absorbed or reflected. Point it at a comet's coma and you get spatial maps of gas distribution, dust scattering properties, temperature gradients. So what can they capture during the October 1st through 7th window? Time series spectra. That means measuring the coma composition repeatedly over several days, watching how it changes as 3I Atlas approaches the Sun and heats up. If there are episodic outbursts, those brightness variations that ground observers have been reporting, the Mars orbiters might catch them in the act. A sudden spike in carbon dioxide, or water, or carbonyl sulfide, a localized jet turning on and off. That's the kind of data that tests the thermal wave model, the patchy nucleus model, all the hypotheses we've been building. They can also measure dust scattering phase curves. As the geometry between the Sun, the comet, and the spacecraft changes, the brightness of the dust changes depending on the scattering angle. Forward scattering dust, small particles that scatter sunlight preferentially in the forward direction, looks brighter when you're viewing the comet with the Sun behind it. Backscattering dust behaves the opposite way. By measuring brightness at different phase angles, you constrain the dust grain size distribution, which tells you about the nucleus surface properties and how violently it's shedding material. But here's what they can't do: resolve the nucleus. Even at 30 million kilometers, a nucleus that's at most 5.6 kilometers across is a tiny, tiny target. Mars Express's best imaging camera has a resolution of about 10 meters per pixel at the Martian surface from orbit. At 30 million kilometers, you're talking hundreds of kilometers per pixel. The nucleus is a point source, indistinguishable from a star. The coma might be resolved, might show spatial structure, brightness gradients, maybe even hints of jet directions, but the nucleus itself stays hidden. They also can't catch fast microjets or transient features below their cadence. These instruments weren't designed for rapid time series observation of moving targets. They were designed for slow, methodical scans of the Martian atmosphere and surface. You can repurpose them, sure, but you're limited by data rates, pointing agility, and how much time the mission operations team is willing to allocate. This isn't a dedicated flyby mission with instruments optimized for 3I Atlas. It's an opportunistic observation with tools designed for something else. Data paths are also a consideration, and they matter more than you might think. The orbiters don't have continuous contact with Earth. They store data on board and downlink it during scheduled communication windows. That means there's a lag, hours, sometimes days, between when an observation is made and when it reaches Earth. Then there's calibration. Raw spectroscopy data needs to be processed, wavelength calibrated, background subtracted, compared against reference spectra. That takes time. So even if TGO captures something dramatic on October 3rd, we might not see the calibrated results until mid-October, or late October, or even early November. ESA has been clear about this in their frequently asked questions pages. Observations are planned, data will be collected, results will be shared when ready. No promises of real-time updates, no live feeds. Just patient, systematic science happening on the timeline that science requires. There are other assets at Mars, though their involvement is less certain. NASA's MAVEN orbiter studies the Martian upper atmosphere and how solar wind strips it away. MAVEN has ultraviolet instruments that could potentially detect emissions from 3I Atlas's coma, atomic hydrogen from water dissociation, carbon lines, oxygen, but MAVEN's instruments are optimized for faint extended sources like atmospheric glows, not point sources like comets. It's unclear if they'll participate. Mars Reconnaissance Orbiter, or MRO, has high-resolution cameras, but again, at 30 million kilometers, resolution doesn't help you much. MRO could potentially catch the comet as a point of light, confirm its position, contribute astrometry. Same with Mars Odyssey. But none of these missions have announced firm observation plans, so we're in maybe if time and geometry allow territory. Here's a speculative but intriguing possibility. If 3i Atlas has a major outburst during the Mars observation window, something dramatic enough to change its brightness by a magnitude or more, the Mars orbiters could catch the chemical signature, a sudden flood of carbon dioxide or a burst of water vapor appearing for the first time, or trace species like sulfur dioxide or ammonia that weren't detected before. That would be gold. That would tell us the nucleus isn't homogeneous, that there are buried volatiles or pockets getting exposed. It would support the heterogeneous crust model and rule out simpler, uniform composition scenarios. And then there's JUICE, Jupiter Icy Moons Explorer, a European mission currently en route to Jupiter but still relatively nearby in the inner solar system. JUICE might attempt distant observations in early November, after 3i Atlas passes, perihelion. But JUICE's instruments are designed for Jupiter and its moons. Observing a small comet from tens or hundreds of millions of kilometers away, that's marginal at best. And even if they try, the data won't arrive quickly. JUICE's downlink latency means results might not be released until 2026. The practical upshot: Mars is our forward operating base for early October. When ground-based telescopes can't see, when even space-based assets in Earth orbit struggle with solar elongation, the Mars orbiters are our eyes. They won't show us everything. They won't give us the dramatic close-up images that make for good press. But they'll give us chemistry, time series evolution, confirmation, or refutation of models. And in science, that's what matters. But they also introduce a new problem, the data gap. When Mars finishes its observations, and Earth-based assets still can't see because of solar glare, we enter a blind spot that lasts weeks. And that blind spot, that lack of real-time confirmation, is where speculation thrives. So, what happens during the blackout? What could happen to 3i Atlas when nobody's watching? And why is that both a scientific headache and a conspiracy theorist's dream? Part 9. Solar Glare Blackout and the Cloak of the Sun. Late September through November 2025, 3i Atlas approaches perihelion on October 30th, and for most of that time, Earth can't see it clearly, or at all. This is solar conjunction. The term sounds technical, but the concept is simple. The comet passes too close to the Sun from our perspective. The solar elongation, the angular distance between the comet and the Sun in our sky, drops below the threshold where ground-based telescopes can safely observe. Point a telescope too close to the Sun, and you either saturate your detector with scattered sunlight, or worse, you risk damaging the optics. Even space-based telescopes have sun-pointing constraints. Hubble won't look. Within 50 degrees of the Sunday JWST with its giant sunshield is even more restrictive, so we go blind. Not completely, not instantaneously, but progressively. Through September, observations get harder as the elongation shrinks. By mid-October, most ground-based assets have lost the target. By perihelion on October 30th, only specialized solar observatories can see it, and even then, only in limited ways. This has happened before. Sun-grazing comets, comets that pass extremely close to the Sun, often diving into the corona, peak in brightness right when Earth-based telescopes can't observe them. Comet Ison in 2013 was a famous case. It was supposed to be the comet of the century, brightening spectacularly as it grazed the Sunday. But when it reached perihelion, it fragmented and faded, and much of that drama happened while Earth's view was blocked. We only saw the aftermath. The disintegration itself was witnessed by SOHO and Stereo, solar observatories that can handle the glare, but their low-resolution cameras couldn't capture fine details. 3i Atlas isn't a sungrazer. Its perihelion at 1.4 AU is well outside the danger zone for tidal disruption. But the principle is the same. The most interesting moment, when solar heating peaks and volatile activity should be at maximum, happens while Earth is largely blind. So, What can still see during this window? SOHO, the Solar and Heliospheric Observatory, has coronagraphs that block the sun's disk and image the surrounding corona. If 3i Atlas is bright enough and positioned correctly, SOHO might catch it as a point of light moving through the field of view. But SOHO wasn't designed for cometary spectroscopy. It's designed to watch solar wind, coronal mass ejections, sun-diving comets. Its spatial resolution is coarse, its spectral capabilities limited. You'll get broad brush dynamics. Did the comet brighten? Did it fade? Did it fragment? But not chemistry, not fine structure. Stereo, Solar Terrestrial Relations Observatory, consists of 2 spacecraft that view the sun from different angles. Stereo could provide a stereoscopic view of 3i Atlas during conjunction, helping to constrain its 3-dimensional position and motion. But again, low resolution, limited spectroscopy. You're seeing the comet's behavior in silhouette against the solar background, not in detailed color. The Parker Solar Probe, which is diving through the sun's corona on its own mission, has cameras, but they're designed for solar imaging, not distant comets. Same with Solar Orbiter. These are billion-dollar missions optimized for studying the sun, and while they might catch 3i Atlas in passing, it's not their priority. So here's the situation. From late October through November, our view of 3i Atlas is degraded to the point where we're seeing shadows, not substance. We're inferring behavior from indirect measurements, and that leaves room for a lot to happen off-camera. Consider the possibilities. Fragmentation. If the nucleus is weakly bound, if it's a rubble pile held together by self-gravity and ice, the thermal stresses at perihelion could crack it apart. We've seen this before. Comet Shoemaker-Levy 9 broke into multiple fragments before hitting Jupiter. Comet Schwarzmann-Wachmann 3 split into dozens of pieces over multiple perihelion passages. If 3i Atlas fragments, we won't know until December when we reacquire the target. We'll see multiple pieces instead of one, or a diffuse cloud instead of a compact coma. That would answer a lot of questions about internal structure, but it would also mean the end of the object as a single coherent target. Rapid rotation change is another possibility worth considering. Outgassing jets can act as torque sources, spinning up or spinning down the nucleus. If 3i Atlas has asymmetric jets, and they fire at perihelion when we're not watching, the rotation state could change dramatically. We'd see that in the light curve post-blackout, a different period, a different amplitude, indicating that the nucleus is tumbling differently than before. Non-gravitational kicks are the big one, the measurement everyone wants after perihelion. If the comet vents gas asymmetrically, it accelerates. That acceleration changes the orbit slightly, fractions of a kilometre per hour, but over weeks and months, it accumulates. By comparing pre-perihelion astrometry with post-blackout positions, we can measure the kick and infer the outgassing pattern. If the kick is consistent with observed gas production, case closed, it's a comet. If the kick is too large, or in the wrong direction, or can't be explained by plausible jets, then we have a problem. A good problem, scientifically, but a problem, or nothing happens. The comet could glide through perihelion uneventfully, brightening and fading in a smooth, predictable way, with no drama, no surprises. That's actually the most likely scenario, but it's the least exciting, so it gets the least attention. Media dynamics during the blackout will be fascinating to watch. With no new data coming in, with institutions unable to provide updates because there's nothing to update, the narrative space fills with speculation. Old images get recirculated. Anomaly hunters pick apart every pixel of pre-blackout observations. The Quantico connection gets rehashed. Avi Loeb probably tweets something provocative. And by the time we reacquire 3i Atlas in December, the story will have grown in the telling, accumulating layers of interpretation and inference that may or may not match the reality. Here's my advice. Set your expectations now. The blackout is real. The data gap is unavoidable. Whatever happens at perihelion, we won't know immediately. We'll get breadcrumbs from Mars, maybe some coarse dynamics from solar observatories, and then we'll wait. Early December is when Earth-based assets can repoint and start collecting data. Again, Hubble and JWST could submit target of opportunity proposals if the object is still interesting enough. Ground observatories will pick up the trail, and then, weeks after perihelion, we'll start to piece together what happened. If 3I Atlas survives intact and shows a post-perihelion increase in water vapor relative to carbon dioxide, that supports the thermal layer model, deeper ices getting unlocked by heat penetration. If it fragments, we learn about its structural strength and internal composition. If it exhibits strong non-gravitational acceleration, inconsistent with outgassing, the exotic hypotheses come back into play. But here's the uncomfortable truth. By the time we have answers, the most dramatic moment will have already passed, unseen. Perihelion happens in the dark, observationally speaking. And that's just the nature of orbital geometry. The sun doesn't care about our viewing schedules. Post-blackout, if 3I Atlas brightens atypically, or if those anti-tail illusions reappear with different geometry, expect the wrong-way tail narratives to reignite. People will see what they saw before and assume it's the same phenomenon, even if the underlying geometry has completely changed. That's why time-stamped, geometry-corrected analysis matters. An image without context is just a Rorschach test. The viewer assignment during the blackout: be patient. Resist the urge to fill silence with speculation. When someone posts a leaked perihelion image, ask for metadata, ask for confirmation, cross-check against official channels. Most of what circulates during information vacuums is noise. The signal comes later, slower, but more reliable. And when the signal does come, when we reacquire 3I Atlas in December and start getting fresh data, we'll need a framework for interpreting it. We'll need hypotheses to test, predictions to check, a decision tree that helps us navigate from observation to conclusion without getting lost in the weeds. So, let's build that framework now. Let's lay out the competing explanations: natural, exotic, hybrid, and bonkers, and specify what evidence would support or refute each one. Let's turn speculation into testable science. Part 10. Hypothesis Bank: From Natural to Exotic. Science works by proposing explanations and then trying to break them. You don't prove a hypothesis true, you fail to prove it false. So here's our lineup, from the mundane to the extraordinary, with predictions for each. Start with the baseline, the most conservative explanation consistent with the JWST data, the carbon dioxide-driven comet hypothesis. This says that 3I Atlas formed in an interstellar environment where carbon dioxide ice was more abundant than water ice. Maybe its parent star had a different carbon-to-oxygen ratio than our Sunday. Maybe it condensed in the outer colder regions of a protoplanetary disk, where CO2 froze out preferentially. The high CO2-to-water ratio isn't a sign of anything exotic. It's a sign of alien chemistry in the literal sense. Chemistry from another stellar system. The prediction here is straightforward. Strong carbon dioxide emission bands will persist through perihelion and beyond. Water should remain subdued relative to CO2, possibly increasing slightly post-perihelion as solar heating penetrates deeper layers, but never dominating. Episodic jets are plausible due to patchy surface composition and rotational modulation. Non-gravitational accelerations should be consistent in magnitude and direction, with observed outgassing. No steering, no coherent thrust pattern, just chaotic venting. How do you falsify this? If water suddenly becomes dominant without a corresponding increase in solar heating, that's weird. If non-gravitational accelerations exceed what the observed gas production can explain, that's a problem. If the carbon dioxide vanishes entirely and is replaced by something else, we need a new model. Move to the layered nucleus hypothesis with thermal bottleneck. Here, the composition is still natural, but the structure is heterogeneous. The nucleus has an outer crust of carbon dioxide-rich ice and dust, acting as an insulator. Beneath that layer, there's water-rich ice that hasn't been exposed to sunlight yet. As the comet approaches perihelion, solar heating creates a thermal wave that propagates inward at the speed of heat conduction through ice, slow, on the order of centimeters per hour. The CO2 sublimates first because it's on top and because it has a lower sublimation temperature. The water comes later, once the heat wave reaches deeper layers. The prediction shifts: carbon dioxide dominance pre-perihelion, then a transition phase around or after perihelion, where water vapor increases significantly. The CO2 to H2O ratio should drop from 8 to 1 towards something more typical, maybe 2 to 1 or 1 to 1. Post-perihelion observations in December and beyond should show stronger water bands. Light curve might change as new areas of the surface become active and old areas crust over. Falsification comes if the chemistry stays static. If CO2 remains dominant months after perihelion, when the thermal wave should have unlocked subsurface water, then this model doesn't work. If there's no transition, no evolution in composition, we're back to the simple CO2-rich comet hypothesis, or we need something more exotic. Then there's the large dust grains and anti-tail geometry hypothesis. This addresses the visual weirdness, the sunward plumes, the unusual tail structures, without invoking exotic physics. The nucleus is shedding large dust grains, millimeter to centimeter sized, that don't get pushed away by radiation pressure as efficiently as smaller grains. They follow the comet's orbital path more closely, spreading out along the trajectory. From certain viewing angles, this creates the appearance of a sunward tail or spike. It's all geometry, and, viewing perspective, no propulsion required. The prediction: the sunward features should appear and disappear depending on phase angle. As the Earth-Comet-Sun geometry changes post-blackout, the features should evolve in predictable ways. If you model the dust trail in 3 dimensions and project it onto the sky at different dates, the morphology should match observations. Spectroscopy of the tail should show dust continuum, not gas emission, reflected sunlight scattering off particles, not fluorescence from molecules. Falsification: if the sunward feature persists regardless of viewing geometry, if it shows gas emission rather than dust scattering, if its morphology changes in ways inconsistent with ballistic dust dynamics, then it's not just geometry. Then we need a different explanation. Now we push into less common territory with the cryovolcanic pockets or chemically unusual ices hypothesis. Maybe 3I Atlas has pockets of volatiles trapped beneath the surface, subsurface cavities or fractures filled with highly pressurized ices. When surface sublimation exposes these pockets, they burst open, releasing sudden plumes of gas with unusual composition. We're talking about trace species we haven't seen yet: sulfur compounds, nitrogen compounds, hydrocarbons. Things that hint at exotic chemistry or even biological precursors, though biological is a stretch. Predictions get more specific: sporadic outbursts that correlate with new surface areas being exposed to sunlight. Time series spectroscopy should catch transient features, emission lines that appear for hours or days and then vanish. These outbursts might be asymmetric, creating directional jets that cause measurable orbit changes. The trace chemistry should be reproducible across multiple observations, not just one anomalous detection. Falsification: if outbursts don't correlate with surface exposure, if the chemistry is boringly normal, if there are no transient features in the spectra, then we don't need pockets. We can explain everything with standard sublimation from a homogeneous or patchy surface. The embedded ballast jets mimicking control hypothesis is where we start flirting with intentionality. Suppose the nucleus has jets that fire in a repeatable, controlled pattern, always from the same locations, always at the same rotation phase, creating non-gravitational accelerations that look less random and more systematic. Not because there's technology, but because the nucleus's shape, rotation state, and volatile distribution happen to create a quasi-stable jetting pattern. It looks like control, but it's emergent from natural processes. Predictions become testable. Non-gravitational accelerations should be phase-locked to the rotation period. If the nucleus rotates every 14 hours, and jets fire every 14 hours at the same rotation phase, you'd see coherent repeating thrust. The magnitude should still be consistent with gas production. You're not getting more thrust than the mass ejection allows, but the directionality would be suspiciously neat. Astrometry should show systematic orbit changes that are too regular to be random outgassing. Falsification: if the jets are chaotic, if they fire at random times with random directions, if there's no phase locking, then there's no control, apparent or real. It's just a comet doing comet things. Now we enter speculative territory that most scientists won't touch, the hybrid hypothesis of natural nucleus with technological shell or interior. Suppose 3I Atlas is fundamentally a natural comet, a chunk of ice and rock from another star system, but it's been modified. Maybe it's been hollowed out and repurposed as a vessel. Maybe there's a shell or embedded structure that's not natural. The bulk composition looks comet-like because most of it is comet material, but the details don't quite fit. Predictions become exotic. Emissions or signatures that don't match the expected porosity and density of complex ice. Radio reflections or radar cross-sections that suggest internal voids or metallic structures. Light curves with harmonics or periodicities that aren't consistent with a simple rotating rubble pile. Trace elements in the spectra that shouldn't be there. Manufactured compounds, industrial byproducts, things that scream artificiality. Falsification. If every measurement is consistent with natural ice and rock, if radar soundings show homogeneous density, if there are no anomalous spectral features, then there's no shell, no interior modification, it's just a comet. The technological artifact hypothesis with deliberate mission profile is Avi Loeb. Territory. The trajectory looks intentional. The Mars flyby, the perihelion timing, the sequential planetary encounters, it all feels designed. Maybe 3I Atlas isn't a comet at all, or it's a comet being used as camouflage for something else. Maybe it's a probe, either actively controlled or following a pre-programmed trajectory, sent by an intelligence that wanted to study multiple planets in one pass. Prediction becomes stark, non-gravitational accelerations that cannot be explained by outgassing. Period. If you measure thrust that's too large, or in directions inconsistent with any plausible jet configuration, that's your smoking gun. Alternatively, radio emissions, structured signals, modulation patterns, anything that suggests communication or telemetry. Anomalous light curve behavior, periodic flashes, brightness variations with unnatural harmonics, geometric occlusion patterns suggesting a non-spherical, non-natural shape. Falsification. If all accelerations match outgassing models, if there are no radio signals, if the light curve is completely consistent with a rotating comet nucleus with patchy activity, then there's no probe. It's natural. Finally, the fringe. New physics with dark matter drag or radiation anomalies. Maybe 3I Atlas is interacting with something we don't fully understand. Dark matter density in the solar system, modified gravity effects, radiation pressure anomalies. Maybe its trajectory or brightness shows systematic deviations that can't be explained by conventional physics or cometary behavior. This would require not just anomalous data, but anomalous data that's reproducible across multiple instruments and observation sites. Predictions break physics. Systematic residuals in the astrometry that don't correlate with outgassing. Brightness changes that violate energy conservation or thermodynamics. Spectral features that don't correspond to any known molecular transitions. Basically, things that break physics as we know it. Falsification. Conventional physics explains everything. Any apparent anomalies turn out to be measurement errors, calibration issues, or insufficiently modelled natural processes. The falsifiers for exotic hypotheses are clear and achievable. Precise post-perihelion astrometry that matches standard outgassing models kills most exotic scenarios. Null radio detections from sensitive instruments like the Very Large Array or the Allen Telescope Array rule out artificial transmissions. Chemistry that remains squarely within the bounds of known cometary volatiles. No synthetic compounds, no industrial signatures, keeps us in natural territory. The key is being willing to accept boring answers. If 3I Atlas turns out to be a chemically unusual but entirely natural comet, that's still fascinating. It tells us about planet formation in other stellar systems, about the diversity of protoplanetary disk chemistry, about how our solar system compares to others. You don't need aliens to make this interesting. But if the data doesn't fit, if there are anomalies that survive scrutiny, then we follow the data wherever it leads, even if it leads somewhere uncomfortable. And the tests are coming. The Mars flyby is happening now. Perihelion is less than a month away. Post-blackout observations start in December. Every one of those windows is an opportunity to narrow the hypothesis space, to rule things in or out. So let's talk about what to watch for, starting with the event that's happening as you listen to this, the Mars encounter. Part 11. Mars Flyby. What to watch for. October 3rd, 2025. Right now, as you're listening to this, 3i Atlas is making its closest approach to Mars at approximately 0.19 astronomical units, roughly 30 million kilometers. The ESA Mars orbiters, Mars Express, and the ExoMars Trace Gas Orbiter are conducting their observation campaign. This is it. This is the window. So, what should we be watching for in the data releases over the coming weeks? What measurements would be meaningful? What would constitute a surprise? Start with spectral evolution, because this is first and foremost a chemistry story. The JWST preprint gave us a snapshot from August. Carbon dioxide dominant, CO2 to H2O ratio around 8:1. Trace amounts of carbon monoxide and carbonyl sulfide. But that was when the comet was farther from the Sun, less active. Now, as it's heating up and approaching perihelion, does the composition shift? If the layered nucleus hypothesis is correct, we might start seeing more water vapor as solar heating penetrates beneath the CO2-rich crust. The ratio might drop from 8:1 toward 5:1, 3:1. That would be significant. It would tell us that water ice is there, just buried, and that thermal evolution is unlocking it. Alternatively, if CO2 remains absolutely dominant, if the ratio stays high or even increases, that supports the simple chemically unusual comet hypothesis. No hidden layers, just a comet that's fundamentally CO2 rich all the way down. Trace species matter too, more than they might seem. Carbonyl sulfide, OCS, was detected in the JWST spectrum. Does its abundance change? Do new species appear? Sulfur dioxide, ammonia, methane, any sulfur or nitrogen? Chemistry would tell us about the reducing or oxidizing conditions in the comet's birth environment. Any organic molecules, even simple ones like formaldehyde or methanol, would be interesting for astrobiology, not because they indicate life, but because they're building blocks. Isotopic ratios are the holy grail, but they're hard to measure. The ratio of deuterium to hydrogen in water, D to H, tells you about temperature and radiation environment during formation. The carbon-12 to carbon-13 ratio does the same for carbon chemistry. If TGO's instruments have the spectral resolution and sensitivity to detect isotopic variations, that would be publishable in nature-level journals. It would be a direct fingerprint of the comet's stellar birthplace. Dust morphology and phase angle effects come next. As the Mars orbiters observe from different geometries over the October 1st through 7th window, the phase angle, the Sun-Comet observer angle, changes. That lets us test the anti-tail hypothesis. If the sunward plume or unusual tail structures are purely geometric effects, they should change in predictable ways. Dust that looks like it's pointing sunward at one phase angle should look more conventional at another. If the morphology doesn't change consistently with phase angle, if the sunward feature persists regardless of viewing geometry, that's harder to explain with simple dust dynamics. You'd need jets with unusual directionality, or dust with unusual scattering properties, or something else. The Omega instrument on Mars Express can build up spatial maps of the coma. If there are localized jets, regions where gas and dust production is concentrated, Omega might resolve them as brightness enhancements in specific directions. That would tell us the nucleus has active areas and inactive areas, supporting the patchy surface model. Non-gravitational acceleration probe is more subtle, but potentially more important than anything else. Astrometry, from before the Mars encounter, combined with astrometry during and after, lets us fit the orbit with high precision. Any deviations from a purely gravitational trajectory, small accelerations caused by outgassing jets, show up as residuals. The key question, do the residuals make sense given the observed gas production? If you're seeing strong carbon dioxide emission, and the comet is venting asymmetrically, you can calculate how much thrust that should produce. The math is straightforward: momentum conservation, rocket equation basics. Does the measured acceleration match the predicted acceleration? If yes, it's a comet. If no, we have questions. The Mars encounter is useful here because it provides a long baseline of observations in a short time. Mars Express and TGO can take repeated position measurements over days, constraining the orbit more tightly than Earth-based observations alone. Any anomalous acceleration should show up clearly in the residuals. Cross-asset triangulation matters, if we get it. If MAVEN, Mars Reconnaissance Orbiter, or Odyssey contribute observations, and it's not clear if they will, since nothing's been officially announced, we get additional data types. MAVEN's ultraviolet instruments could detect hydrogen Lyman alpha emission from the coma, which traces water dissociation. If water vapor is present but not showing up strongly in the infrared spectra from TGO, UV detection could still catch it. MRO's cameras could provide independent astrometry, confirming the comet's position and motion. Odyssey's thermal imagers could measure the temperature of the coma dust, constraining grain sizes and albedo. The more independent measurements we have, the less likely we are to be fooled by instrumental artifacts or calibration errors. Cross-validation is science's immune system. Directional jetting and geometry offer a speculative but intriguing possibility. If 3i Atlas has jets, and those jets happen to be firing toward or away from Mars during the encounter, the geometry might give us a better look at the jet structure than we'd get from Earth. It's unlikely. Jets are usually tied to solar heating, so they point in sun-related directions, not Mars-related directions. But if there's any asymmetry in the activity, the Mars vantage point might catch it differently than Earth does. If there were directional jetting toward Mars, that would look weird. Really weird. It wouldn't be evidence of targeting, comets don't aim, but it would be worth flagging and investigating. More likely, any jets we see will be sunward or anti-sunward, tied to the sublimation pattern as the nucleus rotates. The value of a null outcome shouldn't be underestimated. If the Mars observations show a completely boring pass, composition consistent with JWST, dust behavior normal, no surprises, no anomalies, that's actually valuable. A boring result narrows the hypothesis space. It rules out exotic behaviors. It tells us that 3i Atlas is behaving like a comet should behave, just with unusual chemistry. Science isn't just about discovering anomalies, it's about establishing baselines. If 99% of what we see is normal, and 1% is weird, we know where to focus our attention. We don't waste time chasing ghosts in the data. Expected lag in public releases needs to be stated clearly. Don't expect immediate results. Calibration pipelines for spectroscopy are complex. Raw data has to be wavelength calibrated, background subtracted, corrected for instrument response, compared against reference spectra. That takes days to weeks. Then there's internal review within the mission team, coordination with NASA and ESA public information offices, possibly peer review if they're aiming for journal publication. Realistically, we might not see the first calibrated Mars data until late October or early November. Some preliminary results might leak earlier, conference presentations, informal updates on mission blogs. But the rigorous analysis takes time. Don't read delay as suppression. Delay is just the speed of careful science. If you want fast, you get sloppy. If you want rigorous, you wait. What comes next follows inevitably. The Mars window closes on October 7th or so. After that, the comet continues inbound toward perihelion on October 30th. Earth-based assets lose view. Solar observatories might catch glimpses, and then we wait for December. But before we get to December, before we talk about what happens post-blackout, we need to address the most dramatic moment in 3i Atlas's journey through the solar system. Perihelion itself, the crucible, the furnace, the moment when the comet either survives, disintegrates, or transforms into something else. Part 12. Perihelion Crucible. Survive, disintegrate, or transform. October 30th, 2025. Perihelion. Closest approach to the Sun at approximately 1.4 astronomical units, about 210 million kilometers. That's inside Mars's orbit, outside Earth's. Not a sun grazer, not even close, but still the peak of solar heating for 3i Atlas's entire trajectory through the inner solar system. For a comet, perihelion is the moment of truth. All the volatiles that have been slowly warming, all the subsurface ices that have been creeping toward their sublimation points, All the structural stresses building up as one side bakes and the other stays frozen. Everything comes to a head, and we won't see most of it. We'll be blind, shrouded in solar glare, inferring what happened from before and after observations. So let's game out the scenarios. What could happen? What would each scenario look like? And how would we know the difference? Comet Ison is the cautionary tale, the ghost that haunts every perihelion prediction. In 2013, it was hyped as the comet of the century, predicted to become spectacularly bright as it grazed the Sun at a perihelion distance of just 0.012 AU, less than 2 million kilometers. Ison didn't make it. Somewhere around perihelion, it disintegrated. Tidal forces, thermal stresses, or maybe just structural weakness took it apart. What emerged on the other side was a fading cloud of dust. No coherent nucleus, no future. Could 3I Atlas suffer the same fate? The perihelion distance is much safer, 1.4 AU versus Ison's 0.012. Tidal forces are negligible at that distance. But thermal stress is still real. If the nucleus is a loosely bound rubble pile, if the internal ice matrix that's holding it together sublimates away, the whole thing could come apart. The signatures of disruption would be unmistakable once we reacquire the target. When Earth-based telescopes can see again in December, instead of finding a compact coma with a central condensation, we'd see a diffuse cloud. The brightness would be much lower than predicted. Astrometric solutions would be noisy. Instead of tracking a single point, you're trying to fit an orbit to a debris field. Spectra might show unusual dust-to-gas ratios, with more dust than expected because the nucleus has pulverized itself. If disruption happens, we learn about the structural strength of interstellar comet nuclei. We learn that 3I Atlas was fragile, that its journey through space hadn't fused it into a solid monolith. We lose the chance for long-term study, but we gain data about composition and structure from the debris. It's not the outcome anyone wants, but it's an outcome that teaches us something. Contrast that with the graceful survival scenario. Comet Lovejoy, C/2011 W3, was a sungrazer that survived. It passed within 0.006 AU of the Sun, into the corona, where temperatures hit millions of degrees, and emerged intact, battered, outgassing furiously, but structurally coherent. It brightened dramatically during perihelion, and then faded gradually as it receded. 3I. Atlas isn't facing nearly as harsh an environment, so survival should be the default expectation. Graceful survival means steady or smoothly varying light curve through perihelion. Post-blackout observations in December show a healthy coma, central condensation still visible, spectra showing evolved chemistry, but nothing catastrophic. Non-gravitational accelerations consistent with outgassing. No fragmentation, no sudden changes. This is the boring outcome scientifically, but boring is often correct. If 3I Atlas survives intact, we get months of additional observations as it moves outbound past Venus, Earth, Jupiter. We can track how the chemistry changes as it cools, whether water finally dominates over carbon dioxide, whether the episodic jets settle into a steady state or keep flickering. The chemistry evolution becomes the key testable prediction here. If the layered nucleus model is right, post-perihelion should show increased water vapor. The thermal wave has penetrated deep by now, unlocking buried H2, O the C, O2 to water ratio should drop. If it doesn't, if carbon dioxide stays dominant even after peak heating, then we're dealing with a comet that's just fundamentally CO2 rich, no hidden layers. Then there's the dramatic flare scenario, the outburst event. Some comets have outbursts, sudden, dramatic increases in brightness caused by explosive release of volatiles. Comet 17P/Holmes in 2007 brightened by a factor of 1,000,000 over 24 hours. Nobody saw it coming. Post-facto analysis suggested a subsurface pocket of volatiles was exposed, or a structural collapse triggered massive outgassing. If 3I Atlas has a major outburst at perihelion, the first sign would be reports from solar observatories, SOHO or stereo, catching a sudden brightness surge. Then, when Earth reacquires the target in December, it would be much brighter than predicted. The coma would be larger, more active. spectra might show trace. Species that weren't there before, evidence of deeper material being excavated. An outburst would be scientifically exciting and narratively explosive. It would feed alien tech speculation instantly, because sudden brightness changes look deliberate to people primed for patterns. But outbursts are natural. They happen. They're poorly understood, but they're within the bounds of cometary behavior. To distinguish a natural outburst from something exotic, you'd need to check the energetics. Is the brightness increase consistent with sublimation physics? Can you account for the energy budget with solar heating and volatile release? If yes, it's an outburst. If no, if there's more energy than you can explain with chemistry, then you have a problem. A good problem. What SOHO and stereo can tell us is limited but crucial. These solar observatories will be our only real-time eyes at perihelion. SOHO's LASCO coronagraphs image the corona with occulting disks that block the sun's bright photosphere. If 3i Atlas passes through the field of view, it'll show up as a point or streak of light. Stereo's core instruments do the same from different vantage points. They can't do spectroscopy. They can't measure composition. But they can tell us, did the comet brighten or fade? Did it maintain a compact appearance or spread out? Did it survive? That's not nothing. That's the difference between showing up to the December reacquisition with expectations of a healthy comet versus expectations of debris. It sets the tone for all subsequent observations. The thermal physical stakes are higher than they might seem. At 1.4 AU, the sun's energy flux is about 500 watts per square meter. That's less than what Earth receives at 1 AU, 1,368 watts per square meter, but it's still significant. For a comet that's been in deep freeze for millions of years, this is the hottest it's been since it left its birth system. Heat doesn't penetrate instantly. Ice is a poor conductor. The thermal skin depth, how far solar heating penetrates in a given time, is on the order of centimeters to meters for typical cometary ices. That means the surface heats quickly, sublimates, maybe crusts over with a lag of refractory dust. But beneath the surface, the temperature gradient is steep. Deep interior ices stay cold for days or weeks, even as the surface bakes. This is why we expect delayed effects. Water vapor might not spike until after perihelion, when the thermal wave has had time to reach buried H2O-rich layers. The peak of activity might not coincide with the peak of solar heating. There's hysteresis, a lag built into the system. If 3i Atlas behaves as expected, if it brightens steadily as it approaches perihelion and then fades smoothly afterward, thermal physics explains everything. If it spikes or drops abruptly, if there are discontinuities in the light curve, we need structural explanations. Fragmentation, outbursts, rotational changes. The testable predictions for each hypothesis become crystal clear at this point. Disruption scenario. Post-blackout observations show faint, diffuse emission with no central condensation. Orbital solution is uncertain or impossible to fit. Spectra dominated by dust continuum, minimal gas. Survival scenario. Compact coma, central condensation, gas-dominated spectra, with chemistry evolved from pre-perihelion state. Smooth light curve, non-gravitational accelerations consistent with outgassing. Outburst scenario. Brightness much higher than predicted. Large active coma. Possible new spectral features indicating excavation of deep material. Non-grav accelerations temporarily enhanced. Exotic scenario. Brightness changes that violate energy conservation. Spectral features that don't correspond to known volatiles. Non-grav accelerations inconsistent with any plausible outgassing geometry. The communication reality is something we need to accept now. We won't know which scenario unfolded until weeks after it happens. SOHO and stereo data might give hints in early November. Mars assets might contribute contextual observations. But the full picture waits for December, when Earth-based telescopes can repoint and start gathering photons again. This is the frustration and the fascination of astronomy. The universe doesn't perform on our schedule. The most important moments happen when we're blind. We reconstruct what happened from echoes and shadows, from before and after comparisons, from models that fit the data or don't. If 3i Atlas makes it through perihelion intact, the outbound leg is where we get to test everything. The post-perihelion trajectory takes it past Venus, Earth, Jupiter, opportunities for coordinated observation campaigns, for refining the orbit, for watching chemistry evolve as it cools. That's where the long game plays out. So let's talk about the outbound path, the planetary encounters ahead, and what we can still learn even after the drama of perihelion has passed. Part 13, the narrative gap. Silence, speculation, and story bias. Let's step back from the science for a moment and talk about the story. Because 3i Atlas isn't just an astronomical object, it's become a narrative, a story that different people are telling in different ways. And understanding the narrative is as important as understanding the comet itself, because narratives shape what we believe and how we respond. On one side, you have the institutions, NASA, ESA, the astronomy community. Their story is measured, factual, cautious. Blog posts about Hubble observations, preprints on RAGZEV detailing spectroscopy results, frequently asked questions pages explaining orbital mechanics, press releases that read like technical documentation because, well, they are technical documentation. This is science communication in its traditional form, authoritative, vetted, slow. On the other side, you have the alternative narratives, social media posts, suggesting NASA is hiding something, YouTube videos with ominous music and titles like Comet or Probe, Reddit threads connecting 3i Atlas to Quantico, to UAP reports, to decades-old conspiracy theories about government suppression of alien contact. These narratives are fast, emotionally resonant, built for sharing. They don't wait for peer review. They don't hedge with uncertainties. They tell a story with clear villains and hidden truths. And in between, you have the legitimate speculation. Scientists like Avi Loeb, who are willing to publicly entertain exotic hypotheses, amateur astronomers sharing observations, science communicators trying to explain the actual data while acknowledging the weirdness. This middle ground is where most of the interesting conversation happens, but it's also the hardest space to occupy. You're pulled toward institutional caution on one side and sensationalism on the other. The media ecosystem asymmetry creates the fundamental problem. Caution doesn't go viral. NASA observes unusual but possibly natural comet gets a few hundred clicks. Alien probe approaching Mars, NASA silent, gets hundreds of thousands. The incentive structure of digital media rewards novelty, certainty, and emotional impact. Measured analysis doesn't deliver any of those. So what happens? The sensational claims spread faster and farther than the corrections. By the time an astronomer publishes a detailed rebuttal explaining why the sunward tail is just an anti-tail illusion, the original viral post has been shared 10,000 times. You can't unring that bell. The correction reaches a fraction of the audience that saw the initial claim. This isn't new. This has been true since the printing press, since radio, since television. But social media accelerates it to the point where the correction might not even matter. The narrative becomes self-sustaining, feeding on itself, accumulating layers of inference that become harder to disentangle the longer they go. Persist. Quantico as narrative fuel is the perfect example of how coincidence becomes evidence in the absence of information. There is no public linkage between Quantico and 3i Atlas. None. Reuters covered the gathering. Al Jazeera covered it. The reporting mentions strategic discussions, readiness assessments, routine military coordination. Nothing about space, nothing about comets. But the timing, late September, right as 3i Atlas approaches Mars, creates an association. Human brains are pattern-matching machines. We see two events happening simultaneously, and we infer causation. Politicians meet, comet arrives, therefore the meeting is about the comet. That's not logic. That's narrative construction. But it feels logical because the pattern is clean, and once that association is made, every piece of ambiguity reinforces it. Why won't the military say what the meeting was about? Must be covering up the space connection. Why is NASA so quiet about 3i Atlas? Must be coordinating with the military. Every absence of information becomes evidence for the narrative. The responsible framing, which I've tried to maintain throughout this script, is to acknowledge the events without claiming a connection. Yes, Quantico happened. Yes, 3i Atlas is happening. No, we have no evidence they're related. If future reporting reveals a link, we update. Until then, they're separate stories. But that responsible framing is harder to hold than the sensational one. It requires intellectual discipline. It requires comfort with uncertainty. Most people don't want uncertainty. They want answers, preferably simple, dramatic answers. Confirmation vehicles and priming explain why this particular story resonates. The 1i/Oumuamua debates prime the public for this. Oumuamua's unusual, elongated shape, its non-gravitational acceleration, Avi Loeb's alien light sail hypothesis, all of that created a template. Now, when another interstellar object arrives, people, they map that template onto it. They look for the same beats. Unusual shape, check, wait, we don't actually know the shape. Anomalous acceleration, check, wait, we haven't measured that yet. Institutional silence, check, wait, they're not actually silent, just not sensation. It's pattern matching again. The human brain is optimized for recognizing patterns, even when the patterns aren't there, even when the current object is fundamentally different from the previous one. 2i/Borisov didn't get the same treatment because it looked and acted like a normal comet from the start. 3i Atlas is getting the treatment because it's chemically weird, because the trajectory looks interesting, because we're going to lose sight of it at perihelion. The narrative hooks are there, so the narrative writes itself. Incentives and structures push in opposite directions, and this matters. Institutions avoid overstatement because they have institutional memory. They've been burned before by premature announcements, by data that didn't hold up, by claims that had to be walked back. Caution protects credibility. But caution also looks like suppression. When you're primed to see suppression, content creators, YouTubers, podcasters, bloggers are rewarded for novelty and certainty. A video titled "Comet Mystery Deepens" performs better than Comet Chemistry, somewhat unusual. The algorithm doesn't care about accuracy, it cares about engagement. And engagement correlates with emotional intensity, not epistemic humility. So the incentive structures push in opposite directions. Institutions toward caution, creators toward boldness. And the public, caught in the middle, has to navigate between them without clear guidance about who to trust. Cognitive traps operate at every level of this story, and naming them helps. Cherry-picking, selecting the observations that fit your narrative and ignoring the ones that don't. If you want to believe 3i Atlas is artificial, you focus on the sunward tail, the trajectory, the Quantico timing. You ignore the spectroscopy showing comet normal volatiles, the lack of radio signals, the predictable light curve variations. Argument from ignorance, assuming that if something hasn't been proven false, it must be true. NASA hasn't definitively ruled out artificial origin, therefore, it might be artificial. That's backwards. The default assumption is natural, unless there's positive evidence for artificial. Absence of disproof isn't proof. Conjunction fallacy, assuming that specific detailed scenarios are more likely than general ones. It's an alien probe designed to study multiple planets. Feels more compelling than it's a comet with unusual chemistry, because the first has narrative structure. But narratively satisfying doesn't mean probabilistically likely. Confirmation bias, interpreting ambiguous evidence as supporting your pre-existing belief. If you already think NASA suppresses information, then their cautious communication style confirms that belief. If you already think comets are just comets, then the same communication style is seen as appropriate scientific caution. The evidence is the same, the interpretation differs based on priors. Productive skepticism requires tools and discipline. How do you navigate this responsibly? How do you stay open to genuine anomalies without falling for every exotic claim? Demand provenance. When someone shares an image or makes a claim, ask, where did this come from? What instrument captured it? What's the timestamp, the geometry, the calibration? If those details aren't provided, be suspicious. Prefer multi-epoch data over single spectacular frames. One dramatic image could be an artifact, a processing error, a misidentification. If the same feature appears across multiple observations from different instruments, it's more likely real. Check for independent confirmation. If 3i Atlas shows something anomalous, do multiple observatories see it? Do spectroscopy results from JWST match those from ground-based instruments? Cross-validation kills artifacts and errors. Follow the experts, but don't worship them. Avi Loeb is a credentialed Harvard astronomer, but he's also an outlier in his field. His hypotheses are worth considering, but they're not mainstream consensus. Know the difference between a contrarian hypothesis and established science. Look for falsifiable predictions. 3i Atlas might be artificial is not falsifiable as stated. You can always claim the evidence isn't there yet. If 3i Atlas is artificial, we should see radio emissions or non-gravitational accelerations inconsistent with outgassing is falsifiable. We can test that. If those predictions fail, the hypothesis is weakened. The role of contrarians deserves serious consideration. Contrarians like Avi Loeb serve a purpose. They pressure test the mainstream explanations. They force the community to justify why exotic hypotheses are being rejected. That's valuable. Science needs people willing to say, but what if we're wrong? But contrarians can also become attached to their contrarian position, defending it past the point where the data supports it. There's a fine line between healthy skepticism of orthodoxy and motivated reasoning in defense of a pet theory. The key is to separate the hypothesis from the headline. Loeb's hypothesis that 1i/Oumuamua could be an artificial light sail is scientifically interesting and worth investigating. The headline, Harvard astronomer says aliens visited, is sensationalist and misleading. The hypothesis is tentative, based on limited data, and not widely accepted. The headline makes it sound definitive. Same with 3i Atlas. The hypothesis that it might exhibit non-natural behaviors is worth checking. The headline, Alien probe targeting Mars, is irresponsible. We don't have evidence for that. We have questions, which is different. Narrative stewardship matters for reasons that extend beyond this single object. Why spend time on this meta-level analysis? Because how we tell these stories shapes public trust in science, shapes funding decisions, shapes how the next interstellar visitor gets received. If 3i Atlas turns out to be a completely natural comet, and the speculation was all noise, some people will feel burned. They'll be less likely to engage with the next announcement. They'll be primed to see crying wolf. If, on the other hand, we navigate this responsibly, speculate openly but carefully, demand evidence, update beliefs as data comes in, to acknowledge uncertainty, then we build a model for how to handle future events. We create a culture where it's okay to ask, what if, without immediately jumping to conclusions. That's the goal, not to shut down speculation, but to make it disciplined, not to trust institutions blindly, but to understand why they communicate the way they do, not to dismiss exotic possibilities, but to require that they earn their place in the hypothesis space with data, not vibes. Where to watch and what to trust becomes the practical application. Follow MPC circulars for astrometry. Check JPL Horizons for updated orbital solutions. Read preprints on RxIve, especially those authored by mission team members. Watch for ESA and NASA official posts. They're slow, but they're vetted. Listen to credentialed astronomers who engage publicly, but weight their statements by whether they're representing consensus or personal speculation. Avoid anonymous, leaks, uncited screenshots, and claims without instrument names and timestamps. Be skeptical of dramatic narratives that fit too cleanly. Reality is messy, science is uncertain. If someone is selling you certainty, they're selling you narrative, not data. And remember, the weirdest natural comet ever discovered is still mind-blowing. You don't need aliens to make this interesting. The universe is strange enough on its own. Which brings us to the final question. What should you, the viewer, do with all this information? How should you engage? What should you watch for? And what's at stake in getting this right? These are all questions for another time. Thank you for joining me on this late-night exploration, and good night.